Okay. So circle those atoms who have a lone pair. So lone, because these are the one which can form a dative bond with the transition metal ion. Okay, next part. FeEDDS negative is red and FeEDTA negative is yellow. Okay. Explain why the two complexes have a different colors. And it's of 2 marks. So one, that if both have a different color, which indicates that this gap between the d orbitals when they split is actually differs. Here, for example, one have a smaller energy gap and the other one have a greater energy gap. So my first point will be that the delta E is different for both the complexes. So different frequency of light is absorbed. Yes, is this understandable? That they got a different energy difference between the d orbitals when a different ligand is bond. So each complex absorbs different frequency or a different wavelength of light. Hence, they show different colors. Now, next part. When EDDS4 negative is added to Fe3 positive, the following reaction occurs. Okay. State the type of reaction that occurs. Yes, which reaction it can be? If you see, the complex
The
is
ligand
aqueous.
substitution reaction.
Yeah, good. Ligand substitution reaction. Because both the complexes are in their aqueous state and only the ligand is substituted from the complex. Now, next part. Write an expression for the stability constant K step for FeDDS negative. Okay. So here, if you see, they are not referring to any of the equation. And okay, this is the equation. So how this ligand is forming, if I'll write the equation, initially I have a hexa aqua iron 3 positive complex. And we added EDDS4 negative ligand. It is aqueous. It is aqueous. Now Fe EDDS 4 negative, sorry, 1 negative complexes form and 6 water molecules. So when you have to write the K stability constant, K step constant, anything which is in aqueous must be included in this equation, but not the liquid. So same like Kc, the concentration of the product is written in numerator, and I make one another square bracket for the concentration. Then divided by concentration of the reactants times EDTS. 4 negative. Is this clear? Okay, now next part. The table shows the values for the stability constant of both the complexes. Okay, if you see over here, FEDDS negative have 3.98 exponent minus 2, and FEEDTA have 1.26 exponent minus 20, oh, sorry, exponent 25 and exponent 20. So it's a smaller value, right? And this one is a bigger value. And remember, if it's a bigger value, so it is a more stable complex than the FEEDDS negative. Predict which of the FEDDS negative or FEEDTA negative complexes is more stable. Explain your answer with reference to K step value. So we have already discussed, just we have to state this, that FEEDTA negative is more stable complex because its K step value is greater. Is this understandable? Yes. Okay. When an excess of EDTA4 negative is added to FEEDDS4 negative, sorry, FEEDDS negative, the following equilibrium is established. Calculate the equilibrium constant Kc for this equilibrium using K step values given in the table C5. Okay, here we have given the value of both the complexes. This one is a little trickier. Let's see how we'll do it. I have to do little homework for this. For example, here on the product side, if I'm getting FEEDTA, and I'll do the same thing, like for example, FeH2O6 3 positive is reacting with EDTA4 negative. We are going to get FeEDTA plus 6H2O. And if I write the K, okay, this is the K step for Fe. 1 minute, please. Okay, so this is the K step for Fe EDDS negative. Now if I'll write the K step for Fe EDTA negative, then again I skip the water and I have this expression that FeEDTA negative over Fe H2O6 3 positive and EDTA4 negative. Is this part is understandable to everyone? Yes?
Yes, sir.
Okay. Now they are asking for the Kc. If I write the Kc expression over here, so the Kc expression would be Fe EDTA into concentration of EDDS4 negative divided by concentration of FeEDDS negative into concentration of EDTA4 negative. Okay, what is the issue with Ahmed? Okay, if you see this Kc expression that I have written over here, it have both EDTA, iron FeEDTA complex and EDTA both like as they are over here, right? ये बात समझ में आ रही है? Is this understandable to everyone?
Yes.
And if you look for the K step for FeDDS, this complex and this ligand are basically reciprocal over here, right? That here the complex is in numerator and here that complex is in denominator. Here the ligand is in denominator and that ligand is in numerator. So I can conclude over here, as they say that you have to use the k-step values. So it is basically equals to k-step of Fe EDTA negative over k-step Fe EDDS negative. Is this clear? Yes. Yes, if anyone have any confusion, kindly ask. As this complex is in numerator, that's why I uh, keep the k-step of that same complex in the numerator. And as this complex is in denominator, so I keep its k-step in the denominator. Yes. Is this clear or not? Okay. So I just need to put the Kc expressions over here, or the k-step values over here. So k-step for FeEDTA is 1.26 exponent 25. Divided by k-step of FeDDS negative 3.98 exponent 20. Yes, can anybody tell me the answer?
3.17 exponent 4.
3.17 exponent 4. Okay. They didn't ask for the units. Okay. Let's move to question number 5. Carboplatin and cetraplatin are used as anti-cancer drugs instead of cisplatin. Describe the action of cisplatin as an anti-cancer drug. Yes, can anybody recall or can anybody remember?
It binds with cancer cells.
And what are those cancer cells? Basically, more specifically, we can say it binds with DNA. And then it prevents the replication of that DNA, which actually causing the cancer. So it stops cell division. So cisplatin bonds with DNA and prevent it to replicate further. Is this statement is clear? So you must remember that whenever they ask you the action of any complex transition complex, for, or as an anti-cancer drug, you always write this statement. Suggest the geometry of the platinum center in the carboplatin complex. Here we have a carboplatin complex. So what is the shape or the geometry around this?
Planar.
Square planar, very good, because there are four bonds, and whenever there are four bonds, it can either be tetrahedral or square planar. But remember, for tetrahedral, two bonds are on the plane, one bond goes above the plane and one bond goes below the plane. But if you see, there are two bonds below the plane, two bonds above the plane, sorry, two bonds below the plane and two bonds above the plane, then it's a square planar like this. If you see, two bonds are below the plane and two bonds are above the plane, so it is square planar. Yes, is this understandable to everyone? Okay, now suggest why carboplatin does not show cis trans isomerism. Yes, can anybody suggest why it does not show cis trans isomerism? It's a carboplatin, right? Yes. Any suggestion?
Because of bidentate ligand.
So what happens due to the pidentate ligand? Okay, tell me what is the bond angle over here between these two bonds?
90 degrees.
90 degrees. And what is the bond angle from here till here?
180.
180 degrees. So if I have to bond two ammonia molecules at 180 degree, it is possible because these two are different molecules. But when I have to bond one, because it's a single molecule and both the atoms are at the distance of 90 degree, so it cannot able to bond at 180 degrees. They cannot reach over there at that much distance. Is this understandable? It is not possible. So we may write you are right, Hamna, that it's a bidentate ligand, but we have to further elaborate it that the atoms in bidentate ligand can bond at a distance of 90 degrees but cannot bond at a distance of 180 degrees. Is this understandable to everyone?
Yes, sir.
Okay. Next part. Cetraplatin is a neutral complex containing ligand. Okay. When we have a ethanoetine, the other one is this one, chloride and ammonia. Reduce the oxidation state of platinum in cetraplatin. It's a neutral ligand. Okay, so see, platinum, then CH3, CO2 is bonded to it. C6H11, NH2 is bonded to it. Chloride is bonded to it. And ammonia is bonded to it. And this is the whole complex. And they say as it's a neutral complex, which means that the sum of the oxidation numbers must be equal to 0. If you see over here, the charge on ammonia is 0. The charge on chlorine is -1. The charge on this amine is again 0. The charge on ethanoetine is -1. So the whole charge is 0, which means that the platinum must have a +2 oxidation number. So +2 and -1 and -1 gives you the net charge 0. But let me check again. Okay. There are 2 of chlorine, 1 minute. So wait over here. The net charge is 0. There are 2 chlorine. There is only 1 ammonia. And there are 2 ethanoetines, right? Okay. So it's like this. So here we have a 0. Here I got -1 times 2. Here it is 0. And here I got -1 times 2. So there is net -4 charge. So platinum must have +4 charge. So I will write +4 over here. Is this clear?
Yes.
Okay. Compound M is made from 1,3 dimethyl benzene, and here it is, in a two-step synthesis. Okay. If we see at compound M, we have a 2 chlorines over here, but in compound L, there is no chlorine, but 4 oxygens. Draw the structure of L. So can anybody identify which functional group present in compound L?
Carboxylic acid.
Carboxylic acid, yes, very good. Because if you recall, when we have a carboxylic acid and we treat that carboxylic acid with PCl5 at RTP or SOCl2 at RTP or PCl3 with heating, so OH is displaced by Cl. So it means on these two positions, there must be a carboxylic acid group. So the structure of L, a benzene ring. Here I have a carbon, and that carbon have a carboxylic acid. Here I have a carbon, and that carbon have a carboxylic acid as well. Yes, is this understandable? This OH group is displaced by Cl by using either one out of these 3 reagents. Okay. Now next. Suggest the reactants and conditions for each step of this synthesis. Okay, in step 1, we have basically here a CH3 group and a CH3 group, and they are converting into L, and we have a carboxylic acids in L. So for this, if you recall, we use alkaline potassium magnate 7, then we acidify it. And the other condition for this reaction is to heat under reflux. Now look at step 2. In step 2, we have already discussed the conditions. We can use any one of this. So I will just write PCl5 at room temperature. Yes, is this clear? Okay. Write an equation for step 2. So step 2, if you see in step 2, we have a L that is reacting with, for example, PCl5 forming M. So whenever the reaction is with PCl5, the byproducts we get are PCl3 and HCl. So if I'll write the equation, it's C8H6O4 with PCl5. My product have, if you see over here, instead of these OH, I got Cl. So the formula would be C8. There is no change in carbon. 2 hydrogens are decreased, so H4, and 2 oxygens are decreased, so O2, and then Cl2, because 2 chlorine are attached. It's not 2. POCl3 would form and HCl. So the displacement is actually occurring at 2 different positions. So we need 2 moles of PCl5. So here we got 2 POCl3 and 2 HCl. Now the equation is balanced. Yes, is this clear to everyone? Yes.
Yes, sir.
Okay. Next part. A student investigates a possible synthesis of M directly from benzene using SCOCl2 in the presence of KLCl3 catalyst. Okay, it is related to the electrophilic substitution of benzene. Okay. Benzene initially reacts with COCl2 as shown in the reaction 1. If you see, COCl2 is reacting with AlCl3, forming this positively charged ion, which is actually electrophile, because electrophile are electron deficient. Then in the next step, benzene molecule reacting with this electrophile, and one hydrogen is substituted by COCl. Reaction 2 is electrophilic substitution of this electrophile for hydrogen ion in benzene. Suggest a mechanism for reaction 2. So its mechanism is as same as you practiced with positively charged chlorine or positively charged alkyl group or positively charged acyl group. So our electrophile have a C double bond O and a Cl. And this carbon have a positive charge, right? So what will happen initially? From this pi bond system, there is an attack on this positively charged carbon. We show that attack by a curly arrow. And as a result, we got an intermediate. And in that intermediate, one of the carbon is bonded of benzene is bonded to this group. And that carbon still have a hydrogen. Each carbon have a hydrogen in benzene. At this movement, what we'll do? We will make a semicircle with a positive charge, and then we show the transfer of this pair of electron into the benzene ring. And what will happen then? As this pair of electron is transferred inside the benzene ring, the pi system is again stabilized, and we have a COCl bonded to a benzene ring, and H positive is released. Yes, is this clear to everyone? Yes, if anybody have any confusion, kindly ask. Okay. Question number 6. Fumaric acid is naturally occurring dicarboxylic acid. Okay. Here we have an alkene, a carbon-carbon double bond, alkene, and an acid both. Identify the products of the reaction between fumaric acid and an excess of hot concentrated acidified magnate. If you recall, this reaction is from AS. So whenever we use hot concentrated acidified magnate, the molecule is broken down into two parts, where there is a carbon-carbon double bond. So, and see, there is another important thing, excess. So think, when this is broken down, we are left with a carbon which is bonded to a carboxylic acid, and that carbon have a hydrogen. And the other molecule have a same thing, a carbon that is bonded to a hydrogen, and there is a carboxylic acid. So can anybody identify in which functional group these carbon are going to convert? This is completely AS level knowledge. These reactions you studied in your AS level. Yes, can anybody recall? Yes? No one? These two are going to convert into carboxylic acid. And here we have a rule. See over here. See, if this carbon double bond is going to broken down, if you look at this yellow carbon have a one alkyl chain and one hydrogen. So see, this yellow carbon is converting into carboxylic acid. So there are three different products that can be obtained from an alkene when we heat or reflux the alkene with hot acidified concentrated magnate. See over here, if the double bond is broken down and the carbon which have a double bond have just two hydrogen, that carbon is converted into carbon dioxide. If the double bond is broken down and the carbon which had a double bond is bonded to a carbon chain and a hydrogen, that carbon forms carboxylic acid. If the double bond is broken down and the carbon which had a double bond is bonded to two carbon chains, then that carbon is converted into carbon dioxide. Yes. Is this clear? So if you see here, as the double bond, here we have a double bond. This double bond is broken down, and this green carbon have a one carbon chain and one hydrogen. Same goes with this carbon. So these carbon are going to convert into carboxylic acid. So if these carbon are going to convert into carboxylic acid, then we got one molecule having two carboxylic acid, and there is another molecule of two carbon, and both the carbons are carboxylic acid. Is this understandable to everyone? Yes, Please, if you have any question or any doubt, kindly ask. Yes. Is this clear over here or not?
Yes, sir.
Okay. But
Yes, sir.
so are my products or not? Yes. We are getting ethane dioic acid. But see, what they have mentioned that we are using excess hot concentrated acidified magnate. So what will happen? Initially, acidified magnate convert this compound into two molecules of ethanoic acid. Oh, sorry, ethane dioic acid, right? But we have an excess of hot concentrated magnate. And if you recall from A2, that only two carboxylic acids can be oxidized, right? And what are these two? Methane dioic acid and ethane dioic acid. And if you see over here, we are getting ethane dioic acid. So when ethane dioic acid oxidizes, see over here, our products are carbon dioxide and water. So this would be my answer. Our final products are carbon dioxide and water, because excess of oxidizing agent, that is acidified magnate, is used. But if excess is not mentioned over here, then our answer would be this only. Is this clear?
Yes, sir.
Okay. Now, next part, fumaric acid can form addition and condensation polymer. Okay. Draw a repeat unit of addition polymer of polyfumaric acid. So if you recall, addition polymer is due to carbon-carbon double bond. So if I draw this, I can see there is a carbon-carbon double bond and a carbon-carbon double bond molecule of carbon atom have a carboxylic acid and a hydrogen. The other carbon also have a carboxylic acid and hydrogen. So if I have to draw the repeat unit, what I need to do, I just need to remove this double bond and make two empty bonds on the left and right. Now this is the repeat unit of addition polymer. Yes, is this clear? Yes.
Yes, sir.
Okay. Now, draw the repeat unit of polyester formed when fumaric acid reacts with ethane 1,2 diol. Draw ester bond. Okay, do we have to draw the repeat unit? The ester bond should be fully displayed, should be shown fully displayed. Okay, so if I draw the fumaric acid, that the fumaric acid have a two carbons forming a double bond and a two more carbons which are actually carboxylic acid. So this is the fumaric acid, right? And then we have ethane 1,2 diol, which means, okay, let me do this. It is ethane 1,2 diol. Yes. Give me a minute, please. Okay. So when carboxylic acid and alcohol reacts, what would happen? The OH from the carboxylic acid is removed and the H from the alcohol is removed to form water. And as a result, this O of an alcohol bonds with the C double bond O of a carboxylic acid. So see, a ester linkage is formed. In the same way, because we have to draw the repeat unit, we will remove this H from here and this OH from here. Another water molecule is released and we show the empty bonds on the both sides, and that is your repeat unit when a ethane 1,2 diol reacts with fumaric acid. Yes, is this clear to everyone?
Yes, sir.
Okay. Next part. Explain why polyesters normally biodegrade more readily than polyalkenes. Yes, who have an answer for this?
Because they can be hydrolyzed.
Very good. Because polyester have a C double bond O and that carbon bonded to O, and polyalkenes have a carbon-carbon single bond. This bond can easily be broken due to hydrolysis, where there is no hydrolysis can break carbon-carbon bonds. Good. So here we can write that polyalkenes polyalkenes cannot be hydrolyzed but polyester are broken down due to hydrolysis. Is this clear? Now next part. Fumaric acid reacts with cold dilute acidified magnet to form compound P. So compound P must be a diol C over here OH. What would happen actually when we use these conditions, that carbon carbon double bond is broken down and both the carbons have OH group. So a diol is formed. Only 3 stereoisomers of P exist. Okay. And you see P have a chiral center. One of the stereoisomer is shown. Complete the 3-dimensional diagram in the boxes to show the other 2 stereoisomers. Okay. So if you see, they have given you one hint that one carboxylic acid is actually on the plane. And here if you see, both the carboxylic acids are on the plane. And they have not shown you the positions of H and OH on both the carbon. So the easiest way is to keep the carboxylic acids both on the plane. And if you see here, both the hydrogens are below the plane, right? And both the hydroxides are above the plane. So we just swap these two, means I'll draw both the hydrogens above the plane now and both the hydroxides below the plane now. So this is one of the stereoisomer, and in the other stereoisomer, I only swap the position of these two on one carbon. For example, if I'm keeping the hydrogen and hydroxide over here, like this as given over here, okay? But here I can swap the positions, which means now I keep the one hydrogen above the plane, one hydrogen below the plane. In the same way, one hydroxyl above the plane and one hydroxyl below the plane. So now these are the 2 other isomers. Yes, is this clear?
Sir, how do we know that we have to fix the other carboxylic acid?
Actually, we can do this. See over here. Here, both the carboxylic acids are on the plane, right?
Yes.
And they have given you one carboxylic acid on both the diagrams on the plane, right?
Yes.
And they didn't mention you the position of any of the hydroxyl and H.
Yes.
So that's why I keep both the both the carboxylic acid same plane as given in the diagram, and I just swap the positions of the rest of the groups which are not mentioned where they have to be drawn.
So the possibility that it's above or below the plane, like would it be wrong or is different?
Can you repeat?
Like if the carboxylic acid is on above the plane or below the plane, it's like will it be a wrong isomer or
Uh, can you repeat again, Hamna?
so if we do like the carboxylic acid the same way we did and we place it below the plane or above the plane, so will it be wrong? So
Uh,
in place of OH or H.
I think we can do this, but the thing is that if you see, we obtain this thing from this compound, right?
Right.
And if you see in this compound, the carboxylic acid are still on the plane.
Yes.
And when this reacts with cold dilute acidified magnate, we got this, right?
Yes.
So the OH being added to both the carbon have the possibility to go above the plane or below the plane.
Right.
So that's why we keep both the carboxylic acid on the plane, because they are primarily the uh, our reactant have the same thing.
Right.
Is it clear now?
Yes.
Okay. D part. The enzyme fumarase catalyzes the reaction of fumarate ions with water to form malate ions. Okay. Fumarate ions converting into malate ions, described with the aid of a suitable label diagram. How an enzyme such as fumarase can catalyze the reaction. Okay, so this part is not in the syllabus now anymore. But you can show it like this, that you can make any shape, for example, a bigger shape, that is your enzyme. And with respect to this shape, you can show your reactant, that we call it substrate. Then in the next diagram, what we do in the next step, basically, we can show this, that it is bonded to the enzyme, and that is called enzyme substrate complex. And then we show in the third stage that our reactant or the substrate is separated, and it is actually changed into other products like this. So this is enzyme, and these are products. So you can state this in this way, that the substrate must have a shape complementary to the active site of enzyme, so it can bind with enzyme to form enzyme substrate complex and then as products formed, they are separated. Is this clear?
Yes, sir.
Okay. Now question number 7. Proline, PRO, is a naturally occurring amino acid. Proline is often found bonded to glycine in protein. Draw the dipeptide proline and glycine. Okay. In the previous data booklets, we have the structures of the amino acids in them. But now in the new data booklet or the data sheets that you are going to be provided in the exam, do not have those. So if they talk about glycine, they are going to give you the structure of a glycine. So glycine is a carbon having two hydrogens and a carboxylic acid and NH2. Now what they are saying, draw dipeptide pro and glycine, which means the first amino acid is the proline and the second amino acid is the glycine, and they both would be bonded to each other. So see, okay, let me draw proline first. This is proline over here. So here I have a nitrogen bonded to a hydrogen. And here I have a C double bond O. So this OH is going to be removed. And from this glycine, one hydrogen from the nitrogen is removed, and this nitrogen is bonded to a carbonyl carbon of a proline, and then you repeat the structure CH2 C double OOH. So this is the division from where both the amino acids are bonded. From here till here, this is a proline, and from this NH till OH, this is a glycine. Is this clear? Yes. जी अगर किसी को कोई कंफ्यूजन है तो प्लीज पूछ लें. From here the OH is released, and from here out of these two hydrogen, okay, let me do this way. This hydrogen and this OH is removed, and this nitrogen is actually bonded to this carbon. Okay. Now, name the type of a reaction that forms dipeptide. So a water molecule is released and two molecules joined. So we call it, yes, what we call it? Condensation. Now next part. Proline is able to form a polyproline peptide chain. A section of a polyproline chain is shown. if you see over here, suggest why the secondary structure of polyproline cannot be stabilized by the hydrogen bonding. Yes, can anybody look at the structure and tell the answer, because this answer can be concluded by observing the structure only. And let me draw the proline over here so it might help you. The proline is this structure. Yes, can anybody answer this one? Okay. So if you see, we know what would happening over here, that the OH is getting removed from there and the H is getting removed from there. So if this nitrogen have an H, for example, in the polymer chain, and a carbonyl oxygen faces to this hydrogen, then there would be attraction, and we call that this attraction a hydrogen bond. So, but if you see over here in the polymer, there is no hydrogen bonded to a nitrogen. That's why no hydrogen bond can be formed. So it is because no hydrogen is bonded to nitrogen in polyproline. Yes, is this understandable to everyone? Okay. The reaction scheme shows several reactions of proline. Okay. So see, it have an acid in proline. In proline, there is a amine, right? I am adding an base in it. So there is a acid-base reaction. So what would be the Q? In Q, that the acidic part of the proline is actually reacted with the base. So instead of C double bond O OH, we got C double bond O O negative Na. Right? In reaction 3, acid is converted into alcohol. No other thing is happened, so it means reaction 3 is reduction, and that reduction is actually happened by adding LiAlH4 in dry ether. If you look at reaction 2, this ethanol chloride is reacted with this carboxylic acid, oh sorry, this proline, and we are getting this having 3 oxygens, which means these 2 oxygen does not removed, and this oxygen is, sorry, this oxygen is also being added. So it means it is, this ethanol chloride is reacted with amine, and it's a condensation reaction, which we call it also, we call it addition elimination reaction. So actually R is basically this thing. The hydrogen is removed from here, the chlorine is removed from here, and that C double bond O CH3. So this is R. Now, write an equation for the reaction of proline with NaOH. Okay, we have already discussed the product. See, they have shown you the carboxylic acid in the formula. So it's very easy. You just write NaOH. You made an arrow. Then you repeat the whole organic product. Just don't write CO2H. Instead, write CO2Na. And the H that is released from here bonds with the OH of NaOH, which results in water. Proline has a secondary amine functional group. Secondary amine reacts with acyl chlorides. Okay, see here they have given you the reaction. For example, dimethylamine reacts with RCOCl according to the following reaction. So see, from here the H is released, from here the Cl is released. And this group is bonded over here. So that's what I did. If you see, I removed this hydrogen and this chlorine. 1 minute. This chlorine and bonded this carbon to a nitrogen. And that's what is happening over here. So they are asking you to suggest the skeletal structure of R. Okay. So we have to make the skeletal structure of R, which means I don't need to show these carbons. So 5 carbon structure. Here I have a carboxylic acid. From here, we got a C double bond O and then CH3. See, now compare these two. It's the same as the above one. Yes, is this clear? Okay. Suggest the reagent required for reaction 3. Okay, we have already figured it out. For reaction 3, we need LiLH4 in dry ether. So I may write LiAlH4 in dry ether. Basically, dry ether is the condition, and here they didn't ask for the condition. So if you don't write this, you will get the. Okay. How much is left? It's still too much. I think we should continue it in the next class. Okay. A big paper. So let's see. I'll try to keep the class tomorrow, inshallah. I will inform you in the group. Okay. And tomorrow we have a paper 5 as well, around from 5:15 to 6:15. Okay.
फिर उससे जल्दी कर सकते हैं या इफ्तारी के बाद
वो बहुत सारे स्टूडेंट्स बिजी होते हैं तरावी में और सब में.
अच्छा
मैं चले
ठीक है
कोशिश कर लेता हूँ, करके देख लेते हैं. ठीक है ग्रुप
चलिए
में.
ठीक है सही थैंक यू
ओके, टेक केयर एवरीवन. अल्लाह हाफिज.